These two chambers represent the inside and outside of a biological cell. A phospholipid membrane separates the two chambers. Both chambers contain a potassium salt dissolved in water as potassium ions and anions. The salt is 20 times more dilute on the outside of the cell than the inside, creating a steep concentration gradient. But no ions move down the concentration gradient because the phospholipid bilayer is impermeable to these charged hydrophilic atoms. And despite the difference in salt concentration, the ratio of potassium ions to anions on each side of the membrane equals 1, and the membrane potential is equal to 0 millivolts. The solutions are electrically neutral, so no charge accumulates on the inside or outside of the membrane. Now let's insert a potassium channel into the phospholipid bilayer. This channel allows potassium ions to diffuse down the steep concentration gradient. The corresponding anion does not fit through the potassium channel and is left behind. As a result of potassium movement, the ratio of potassium ions to anions becomes different inside and outside the cell, causing the inside of the membrane to develop a net negative charge. At first, diffusion is the dominant force moving the potassium ions across the membrane, but as the inside fluid becomes more negative, the negative electrical force pulls the positively charged potassium ions back through the potassium channel into the cell. Eventually, the electrical force pulling potassium ions into the cell exactly counterbalances the force of diffusion pushing them out. This is the equilibrium potential, where electrical and diffusion forces are equal and opposite, and there is no net movement of potassium ions through the channel, despite the concentration gradient. The charge difference between the two sides is the equilibrium potential, and for potassium this is approximately -80 millivolts.